All right. Hey, this is section 5.4, or section 4 of chapter 5, and working with the e function, both derivatives and integrals. Memorizing the value of e to a few decimal points would be a good thing to do. So e takes on the value of 2.71828. If you want to know how e is calculated, you could do this summation of 1 over n factorial. That becomes a series that's equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and so on. If you add up all these individual fractions, you will end up getting the value of e. Bye, guys. All right. So this is what your note sheet looks like. E is approximately 2.71828. Keep that in your head. We have done these derivatives before. The derivative of e to the x is e to the x. The derivative of e to the u, where u is some function, would be e to the u times u prime. What we haven't done that we're picking up that is new for this lesson is the integral of e to the x. Well, if the derivative of e to the x is e to the x, the integral of e to the x is e to the x. The only one that works like that. The integral of e to the u will be e to the u plus c. And I'm just going to put a question mark in front of there because typically coming out of that u sub, you will end up with some sort of coefficient in front, and that would be calculated or computed out by doing your u sub. So just the quick derivative work, y prime equals. Well, it is the e to the u type of pattern. So I know that's going to be an e to the u prime. So e to the 7x times the derivative of the exponent gives me 7. Writing it nicely, I get 7 e to the 7x. B, well, it's still the same type of problem as A, only a little messier exponent. Our u in this case is the negative 3x over 4. So I'm going to go y prime equals. It is e to this u value multiplied by the derivative of negative 3 fourths x. So I'd get negative 3 fourths as my multiplier. I'm going to put parentheses so it shows multiplication. And I would probably move this then negative 3 e to the 3x over 4. The negative exponent dropping it to the bottom. Gets a little messier here. Well, this we definitely could move down using the power rule. Or not rule, but power property of natural logs. So remember how we can make some of those natural logs look a little bit nicer by using properties. And in this case, that is a real nice advantage because natural log of e is just 1. Remember, e to something equals e, well, e to the first. So this turns out to be a value of 1 for natural log e. Now I'm down to an equation that looks like y equals x third. That becomes a y prime of 3x squared. Letter D, we want the derivative. So I want f prime, don't I? Well, if I take the derivative of the left, I also need to take the derivative of the right. And this becomes a second fundamental theorem of calculus type problem. Taking the derivative of the antiderivative, they kind of balance each other off. They are inverse functions. So the trick is to substitute in, that will give me a natural log of e raised to the 4x. But the critical thing, don't forget to take the derivative of our upper bound. The derivative of e to the 4x will be e to the 4x times the chain rule, which will produce a 4. All right, natural log of e is 1. This will be a 4x times a 4e to the 4x, giving us 16x e to the 4x. Now let's move on to the ones that are a little bit more difficult integrating. Integrating usually is typically harder than taking derivatives. So since this is not just a nice straightforward integral of e to the x, which we know would be e to the x plus c, instead I see it as e with a little extra, so an e to the u. Well, we know that the integral is going to be e to the u, but remember how I said there might be something that comes out in front of this, some sort of coefficient. Let's see if that happens here. So let's let our u equal 2x plus 1. Then du is equal to 2 dx, but we don't have a 2, so we need to adjust and call this a 1/2 du equivalent to the dx. Integration, let's rewrite this then. We've got an integral of e to the u du. Except for the dx, I didn't quite do that right because there's a 1/2, isn't there? 1/2 du is the substitution for dx. All right, now we're ready to integrate. We have the 1/2 out front. It'll stay there. And the integral of e to the u is e to the u plus c. That'll give me a 1/2 e, replace u with 2x plus 1, add your c. Here's your answer. Not too bad. Letter F. Letter F. Oopsie, sorry about that. That's a nice rainbow day. The main thing that's capturing my eye is this E, and I see something with a fourth power followed by something with a third power. Well, the derivative of a power of 4 will come down to a power of 3, so that enlightens me as to what I should let U be, and let's let U be x to the negative fourth. The derivative du dx multiplied by a dx, bring it up and over. This side, the derivative will be negative 4 x to the third. We have a 3 here. Ooh, let's just bring that 3 out front. So all I have to match up to is an x to the third dx. So over here, I want x to the third dx. Let's get rid of this by division. Divide by negative fourth. So I get negative 1/4 du is equal to an x cubed dx. Now that we know the substitution, this will come over. I'll get 3 times negative 1/4, giving us negative 3/4. The integral of e, this is a u, negative x to the fourth gets replaced with u du. All right, that's not so bad, negative 3/4. The integral of e to the u is e to the u plus c. We did have that negative 3/4 up front. Replace the u portion, so we're back into x's, and that was a negative x to the fourth plus our mighty c. There's your answer. This one looks uglier than the last. They just keep getting better. This would be an e to the 1 over x squared. That would be an e to the x to the negative 2, wouldn't it? Times x to the negative 3, just bringing this up from the bottom. Now, if I let u equal the exponent part of e, it would look like this. And taking its derivative would give me negative 2x to the negative 3 dx there, because this was a du dx. So dx comes up and over. Subtracting 1, when we go into derivatives, we're subtracting 1. That produces this negative 3 for us. All right, we just don't need the negative 2 part, so let's get rid of that by dividing by it. And matchy-matchy, this is great. There is the matchup that we're looking for. Had I written the dx down there, nice. All right, there's the matchup we were hoping for. This equates to a negative 1/2 du, correct? So I'm going to get an integral of e to the u of negative 1/2 du. The integral of that will be negative 1/2 e to the u plus c. Replace back the u with the x's, so we'd have x to the negative 2 plus c. Final answer. On to H. I'm going to clear the screen. All right, H. A whole lot going on here. I would guess that this should be our U. Let's try it. If it doesn't work, we'll guess on something else and switch it up. But I know the derivative of sine. My inclination is the derivative of sine gives me cosine, and that's going to be a wonderful thing. Derivative of sine gives me cosine of 2x. Don't forget to do the derivative of the inside. That produces a 2. And then I get this dx coming over from the left side. Multiply it up. We don't have 2 over here on the problem, so let's correct it with a 1/2. Multiply both sides by 1/2, and we're looking at that. Go over, let's deal with our integral. E to the u, and cosine 2x dx becomes a 1/2 du. That gives us a 1/2 e to the u plus c, a 1/2 e to the cosine of 2x. Oh, darn it, looked at the wrong line. Sine of 2x was what u was. There's our answer. All right, I am going to finish this, let this, oh, this is one where we have to do a definite integral. Let's do it. Okay, I was trying to shortcut, but there are no shortcuts in life, are there? Very seldom. Derivative would give us negative 2 dx. That's a negative 1/2 du equals dx. All right, we are integrating. This becomes an e to the u du with the negative 1/2 out front. And now, because it's a definite integral, we need to update those boundaries. And remember, I put them in when x is 0. I go back to my relationship between u and x, and I'd have negative 2 times x, or negative 2 times 0, which gives me 0. This will stay 0. But what about when x is 1? When x is 1, u becomes negative 2 times 1, which gives us negative 2, which introduces a whole nother problem. Notice how our smaller value is on top. It takes a negative to flip that, correct? So I'm going to flip over my integral, putting my negative out front, and e to the u du. Negative negative makes positive, so now we're sitting with 1/2. Negative 2 to 0 of e to the u du. Integrate that, I have 1/2 of e to the u evaluated from negative 2 to 0. I do not have to go back to x's since we updated these boundaries. So we're going to have a 1/2 e to the start at the top, e to the 0 minus 1/2 e to the negative 2. So I plugged in the 0 first, subtracted, then put in the bottom boundary. The first one will just be 1/2 of 1 because e to the 0 is 1. This will be a 1 over 2 e squared. We will get an answer of 1/2 minus 1 over 2 e squared. Good answer. If you wanted to pull this together, we'd have e squared over 2 e squared minus 1 over 2 e squared. Common denominator, it can write out nicely as e squared minus 1 over 2 e squared. All right, that should help get you through. There is homework that follows this. It is coming from page 357. Have a great